Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, can the robot tidy my house? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is about robot learning and how AI is helping to equip robots with the skills to cope with messy, unpredictable environments like our homes. But first, I'd like to remind you to subscribe to Robot Talk through your favourite podcast provider to make sure you're the first to hear the latest episodes. Another way to find out about new episodes is the email newsletter, which you can sign up to by going to robottalk.org. So, without further ado, it's time for me to introduce this week's guest. I recently had a great conversation with Lerrel Pinto from New York University about using machine learning to train robots to adapt to new environments. This week, I'm talking to Lerrel Pinto, an assistant professor at New York University researching robot learning and decision-making. Hi Lerrel, welcome to Robot Talk.
Hi Claire, I'm excited to be here.
So you lead the General Purpose Robotics and AI Lab at NYU, where you're working on getting robots to generalize their skills and adapt to the messy, unpredictable world we live in. So can you give us a bit of an overview of the research you're doing in your lab at the moment?
Yeah. So the overall goal of our lab is to create what we like to call a general purpose robot. So what that means is a robot that you can show it a problem and then it's able to either use its prior knowledge to solve it or sort of learn how to solve these things on the fly, right? And so imagine you're in your home, you bring this robot in, you want it to clear the dishes or something of that sort. You want this robot to sort of do these types of tasks. Now, to achieve this, there's a whole range of problems that we need to solve. Our lab primarily looks at AI algorithms and how these algorithms can learn from robotic data in these environments. Right. So even from the perspective of data, there are several questions like, how do you get this data? What type of data should we collect? Is it only visual information? Is it proprioception or touch information? Right. So there's all of these questions. And then once you have this data, how do you learn from it? What are efficient sort of architectures to absorb all of this data? Yeah, so we work on a gamut of problems across the space of robotics.
Okay. It's the kind of thing that people just expect robots should be able to do, to just turn up and help you out and follow instructions and kind of adapt to your home environment, but is actually really quite challenging to achieve.
Yeah, it's quite hard. We have been working on this problem for at least 5 years now. And one of the fun parts of doing research is just looking at all the ways a robot can actually fail.
Yeah.
So in one of our recent papers, we had a Sankey diagram of all the ways it could fail. And it ranges from things like the robot not being strong enough. So, for example, when you ask one of our robots to open the fridge door, it applies so much pressure that it tilts from its base. And so it's not able to do that task.
Right.
And then for other problems, because of the sensing, sometimes it just misses objects. So there may be an object right in front of it, but since it was moving too quickly, the object is too blurred, for instance.
Right.
Or if we feed an image through an object detector, sometimes these object detectors also completely miss these objects. So there's a wide variety of failure modes on these robotic systems as well.
Yeah. So as well as having kind of enough data about what the real world looks like to train the robot, you have to deal with it kind of being aware of the own limitations of its hardware.
Yeah. I think we're sort of like in a domain where hardware is changing and improving every day. AI algorithms are also changing and improving every day. And so when you're working at the intersection of hardware and software, there is a sort of cadence in which we have to update the hardware, update the software. For certain types of hardware, certain types of algorithms work better. For other types of hardware, you may have to play around with the algorithmic aspects as well.
Okay.
So yeah, there's a big space of exploration, which is why, again, from a research perspective, it's great to work on these types of problems.
Yeah, definitely. So last year you developed a home robotics system called OK Robot that can pick up and move objects in settings it hasn't encountered before. So can you tell us a bit about this project?
Yeah. So OK Robot stands for Open Knowledge Robot. So the way to think of it is you can give it a command in natural language. And the hope is that by using existing LLM tools or VLM tools, the robot can automatically relate these natural language queries to physically grounded things in the world.
Okay.
So an example for this is, let's say you unbox a robot in your home and you ask the robot, okay, robot, bring me the pack of chips from my dining table to my coffee table.
Mm-hmm.
And the robot will sort of look around the room. It will see the chips. It will identify that, okay, this is the bag of chips that I was asked.
Yeah.
And then it'll go to it. It'll grab it. It'll then look around the room, see where the coffee table is, go to the coffee table, and then drop the bag of chips over there. Right.
Mm-hmm.
The cool thing about the system is you could give it any query. So instead of a bag of chips, you could ask it for a Coke. You could ask it for like a water bottle. You could ask it for like any object that a 2-finger gripper can realistically grab.
Mm-hmm.
In our more later versions, the system also has the ability to explore. And so what this means is, let's say you ask it for a bag of chips and it looks around, it cannot find it. It will actually search around your house for a bag of chips.
Okay.
And this is quite funny because you can like hide your bag of chips in a weird location and the robot just keeps searching around until it gets a glimpse of it. And the moment it gets a glimpse of it, it then, goes straight for it. Yeah. And so when we create these systems, again, I think the goal is to make the system as general as possible, which means that we want to be able to take this robot to anyone else's home and be able to run the system there. So when we ran the OK Robot experiments, we took it to homes all around New York City and ran experiments with a bunch of different objects that were there already at these people's homes. I think that is really important because there's a big difference between using curated objects in a lab-like setting and using real-world objects in a real-world human-like setting. So we also analyzed some of these aspects of how things change when you're in a lab versus in the home. There are several interesting aspects, but one of the more interesting one is the amount of clutter in actual human homes. In a lab, you can easily separate all the objects on the table, create a nice environment for the robot to access these objects. But in a home, folks may just drop all their stuff in a pile on their table, and the robot will still need to solve it. So we often find that in these cases, the robot is not as successful as we hoped it will be.
You mentioned LLM, which is large language model, and VLM. What is that?
Yeah, so VLM stands for Vision Language Model.
Okay.
And now folks also have this new terminology called MLLM, which is Multimodal Large Language Model. And so VLMs and MLLMs are sometimes being used interchangeably now. The key idea is that there's a single sort of model that can both reason about language and about vision at the same time. So you could sort of ask the model, hey, look at this image. Tell me how many cans of Coke are in this image. right? And so it can look at the image and then sort of in natural language, understand the question that's being asked to it, count the number of cans of Coke, and then sort of report that number.
Yeah. Does that also kind of give the robot like a mind's eye? So if I say, find me a bag of chips, it knows what that should look like, and then it's then searching the environment for that kind of image of what the object should be.
Exactly. So the way it works is when it looks around, everything it sees, it adds everything it sees into a memory bank, and it sort of labels everything it sees based on what these VLMs say it is, right? So the example for it is, imagine you take an image, you ask GPT-4o what is in this image, and whatever it says is in this image, imagine I sort of label that description to those points in the image. And I just do this, as I'm moving in my environment, I keep doing this for every object around. So then when I'm asked by a human, okay, where's the bag of chips? I can then go through my memory bank, search for where the bag of chips are, and then go to that.
Okay. In the examples you gave the can of Coke, which is really easy in a sense that it always looks exactly the same, right? It's a clear brand. It's really obvious. Whereas like the bag of chips example, like different brands will have different packaging. So it could look really quite different in different people's homes. So that's in a way a much harder challenge.
Yeah. I think this is a great question. I think this is actually leading up to a frontier in this problem. And the frontier is sort of having an ambiguous description of an object, right?
Yeah.
So another example is you could ask a robot, okay, robot, bring me something to eat. And now there are many things that you may have wanted to eat, right? So how does the robot figure out what is eatable or not eatable? Or what object would you prefer to eat versus someone else prefer to eat? Now, in the case of the bag of chips, it's sort of easier because there are still a smaller space of bag of chips. And so these models are still fairly good at it. But these models can get confused, right? So imagine you draw a bag of chips on a piece of paper and you leave this piece of paper on the dining table.
Yeah.
Now the robot will look at it and be like, oh, that's a bag of chips. Let me grasp this piece of paper and bring it to my human. So I think there's an interesting sort of question of giving the robot an understanding of what you really want, even though you may not say in very precise description what you want.
Yeah. You mentioned testing it in real homes all across New York. I'd be very interested to see how it performs in a house in Japan or Germany, or, how well it would apply to different cultures. Because I appreciate that like different houses in New York are going to be different, but they're all going to be more similar to each other than houses from completely different cultures.
Yeah. I totally agree. I also think that there's a different type of objects as well, right? In different places, the way you would actually describe objects are also different. So for instance, there could be a way in which you're like, okay, bring me the object over there, right? And so like when you say over there, the robot will have to look at what you're pointing at as well. So I think there's the cultural aspect also affects how you describe objects or how you describe what you want someone to do for you. So I think there's both of these challenges. We haven't investigated it yet. We are working with some folks who are in Germany right now. And so hopefully we'll get some more analysis of this soon.
Well, if you want to send a robot to test in my house in the UK, I'd be very happy to oblige.
Yeah. The next time I'm in England, I'll get the robot.
Fantastic. So we talked a little bit about like large language models. Are there other advances in AI and machine learning that are kind of opening up new possibilities in robotics?
Yeah, so there are several examples. So let's start at the level of supervised learning. So supervised learning is a class of learning where a lot of research has been done over the past like 20 years and so on. And so for a lot of problems right now, if you have a data set for that problem, like where you have a data set of the robot solving the problem, you can create a model that you can then run on the robot.
Okay.
So how do you get the data set? You may have a human tell you operate the robot, it does the task, and then you sort of imitate this behavior through a model. So a lot of this technology is already out there, which makes it very easy for roboticists like us to build these systems without having to go into a lot of the algorithmic details.
Mm-hmm.
So one example for this is the transformer architecture. So the transformer architecture is used in the large language models, but we often use them for a robotic problem. So we treat sort of robot data as, if you squint at it, you can say, oh, it's sort of like language. And so we sort of create a language-like version of the robot data, feed it to the transformers, and then use those same architectures. So that's one example. The other example is in vision. There's been a lot of work in 3D geometry and learning 3D geometric information of the scene around you. So imagine you're holding a camera and you're moving around your home. We have tools right now which can very easily reconstruct your room in 3D. And so we use these tools as well. Actually, OK Robot uses this tool internally where as the robot is moving around, using its visual observations, it reconstructs the scene, which is how its memory is stored, actually. So when you see an object in your memory bank, you store information of that object in a 3D location. And so that aspect is really powerful for us.
Yeah, that's really interesting. So we've had a few audience questions. The first one was submitted on the website, and the question is, what is your intuition on why robots find it hard to learn things that are very easy for humans and vice versa?
Yeah, I think there's this thing called the Moravec's paradox, where things that humans think are hard to do, it's easy for AI to do, right? For example, like playing chess, right? It's easy for AI to play chess.
Yeah.
And then the opposite is also true, where the things that we think are so easy, like, picking up an object from a table is sort of so easy for humans to do. But for a robot, this is like multiple decades of research. And I think there are several reasons for this. I think it starts all the way from hardware. So humans have amazing hardware. Our hands are amazing. If you look at our hands versus the hand of a standard robot, there's a big difference in the capabilities of the hand. So there's a big difference on the hardware. And then from the software, if you think about human learning as an evolutionary process where we have learned over, millions of years of evolution, and then even throughout our lifetime, through many, many hours of interaction, the way robots learn is very, very different, right? We're sort of trying to create a new organism from scratch and trying to figure out what its learning architectures should be, right?
Yeah.
And so I think there's a lot of work to be done to figure out how can we do for robots what evolution has done for us in a way. So how can we create the right learning mechanisms in the robots where it can learn very efficiently from data? So these are all open research problems. And so, right now, there are many things that humans find easy that robots find hard. But eventually, in the near future, that may not be true.
We're not being very fair to robots, because if you gave a robot like 10, 15 years to learn, it might be just as good as a human. Like, we spend a lot of time in our childhoods learning how the world works and how to do all of these things. And if you asked a baby to go and pick up a packet of chips for you, they wouldn't do it.
Yeah, that's true. That's true. Humans also have the amazing ability to learn from others as well. So, for example, let's say you're, learning how to play tennis, and you see a coach play. You can sort of very quickly learn how to do it. Whereas for robots, this ability is really hard. It's really hard for robots to look at a different agent, see how they are doing something, and replicate that on itself. So that mode of learning has not been investigated as much as it should be.
Yeah, I wanted to ask you about that actually, because this kind of imitation learning is something we rely on massively as humans. But if a robot doesn't have like a human shaped body, then it's really difficult for it to kind of translate, even if it can understand what it's seeing, to translate that into how its body should move seems really difficult. So do you think that kind of learning is kind of only useful for robots that are at least like, vaguely human, like they have hands and a kind of approximately humanoid shape?
Yeah, I think this is a great question. So maybe just to sort of set the stage here, there's this type of learning which is called imitation learning, where the way you do it is you need to get a human to show you data, and then you train a model to imitate that data. And once that model is trained, you can run that model on the robot.
Right,
now,
okay.
Of course, this assumes that a human is able to collect data for that robot. And so it works well when you have a system with arms, with like fingers, with hands. It also works for systems where it's human compatible. So, for example, like a car, right? You can train a car how to drive by yourself driving the car and recording that information. So I think for either robots that have human form factor or for human compatible operation, this mode works well. Now, there's another class of robots which are very bio-inspired. For example, robot dogs.
Yeah.
Now, for robot dogs, there are other ways of sort of training it. But if you were going down the imitation learning route, there's some really fascinating work on looking at how dogs walk, doing a motion capture of them, and then translating that motion capture information onto the robot. And now you can do that for dogs. You could do it for, I don't know, like a robot rat if you want, a spider, and so on. I think the really hard question is what happens if you have a robot morphology for which there's no real biological counterpart.
Yeah.
One example for this is maybe a drone. If you think of a drone with like 4 rotors around it, a lot of the algorithms over there are not really imitation-like at all. So they have to come up with other algorithms to optimize their movement.
Would it ever be possible to have a robot that does imitation learning the way we do, like just literally watching somebody do something and then translating that?
Yeah, I think there are several challenges right now for this to happen. So the way imitation learning is done now mostly is by doing something called LE operation. So in LE operation, what happens is the human sort of is directly controlling the robot to create data. And so all the data that is being created is in the eyes or in the view of the robot, right? The challenge with watching someone is that you have to understand how to translate things from someone else's view, like a third person view, to your ego view.
Yeah.
And I think this is a hard problem. This is a hard intelligence problem, right? There's also a question of what's the granularity at which you want to imitate this other person, right? So, for example, if I see you grab a cup of coffee, you may grab it on the handle, but I can also grab it, not on the handle, but on the outside of the cup, right? And these both are successfully solving the task. And so I think, what are you actually taking away from seeing someone else solve the task? Is it the fine-grained motor movement? Is it information of how to interact with the object? Is it just the high level of like how to solve the problem?
Yeah.
An example of how to solve the problem is, let's say there's a coffee spill and you use like a white cloth to clean it. And instead of using a white cloth, I can maybe tip the table over, for instance, to get some of this coffee to fall off. And they're both sort of accomplishing the task to some extent.
Yeah, and I guess you need to understand what the goal is to know which bits of the task are relevant.
Exactly. So I think the granularity of what information you're trying to take away from watching someone is, I think, a very interesting question.
Yeah.
It's something that's not been, again, investigated as much.
Okay, we have one final audience question. This was also submitted on the website. What are some prerequisites for working in your area of robotics? I think this is someone who is keen to pursue a career in robotics.
Yeah, I mean, I'm glad to hear that there are folks interested in doing robotics. So I think when you're starting out, the main requirement is just having persistence, I would say. And the reason is that robotics is such a wide field, right? There's no one who has expertise in all of robotics.
Yeah.
And so once you're persistent, you can see the types of things you're interested in, and then learn those things that you need to learn to solve the problems that you want to solve, right? So, example, if you want to work on hardware, you may need to learn about 3D printing. You may need to learn a little bit about sort of engineering, how to build things, and so on. If you're interested in the algorithmic side, you may have to learn linear algebra. You may have to learn deep learning, and so on, right? And so, no one in robotics starts off knowing everything, and it's only after time that we learn how to do these things.
Yeah, absolutely. Lerrel, it's been really fun chatting to you today. I've been speaking to Lerrel Pinto from New York University. Thank you.
Thank you.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And if you've got a question you'd like me to ask one of my future guests, you can contact me on social media at Robot Talk Pod, on Patreon at patreon.com/Claire Asher, or at robottalk.org. I regularly announce upcoming guests on all those platforms, and I'd love to include your questions in my next interview. I thought you might like to hear a sneak peek of this month's bonus episode.
I gave a talk at a grower conference. These were herb growers, mainly field herbs, so they're growing stuff outside. And there's about 70 growers at the show, and there were about 15 companies who were showing their equipment for this sector of the industry. But over half of those companies were either robotic companies or companies with advanced AI applications. Mainly around weeding applications or grading applications. So weeding robots are really there. I don't think there's a fruit and veg grower now who isn't seriously thinking about a robot to control weeds rather than using broadacre herbicides because herbicides are coming down. So to me, that was a really important crossover point where we're seeing more companies that are robotic companies than conventional ag machinery companies. Big breakthrough. And we're getting there on the harvesting piece. Chris is doing amazing stuff with asparagus by the machines. Dogtooth in the UK. I was at a very, very significant farm yesterday looking at their next generation robot. And goodness, it's really close. And the technology in that is very, very impressive. So we crossed over in field machines, robotic weeding. I think we're very close to crossover on harvesting for some of those really difficult crops. And it's only got to be the case where a robot is cheaper than a human picker, doesn't have to be better than, it just has to be cheaper than a human picker. And there will be no reason at all why farmers won't just roll into those technologies. The supply chain adopts technology very, very quickly, as long as it's proven. And that's where we're at. We've got to get to that proven bit, but I think we're quite close.
Brilliant. Chris, do you want to maybe talk a little bit about some of your recent innovations?
Yeah, trying to follow on from what Simon was saying there, covered quite a lot of the latest developments. I think for us with the asparagus harvesting, last year we made a huge jump in field in the testing that we'd done, and we'd gone from 30% harvest success rate with our asparagus harvester to over 85%
Wow.
of detecting actually what needed to be harvested, only selecting that, not damaging anything else, and getting it into a tray ready to be delivered to a pack house. And that's kind of the dedication that the team put in over the winter to improve our models, testing in the lab. Our robots are designed with the field in mind, not with the lab. And Simon, you were saying like if it's cheaper than, but for a lot of the growers we work with, it's not about replacing people, it's about filling a gap that's there already. Then with the kind of seasonal worker scheme that exists, it doesn't have enough places to fill the demand from the industry. But if we can solve harvesting in asparagus, and if Dogtooth can solve harvesting in strawberries, then the available workers that there are can then go to and be redirected to different parts of the industry and just take that pressure off. So we see, yes, there might not be an asparagus harvesting job in 5 years' time, but there's going to be other opportunities for the workers that are available to go and work in.
Yeah.
Well, I think that's a really important point that Chris makes, because I think the danger is that we try and solve all the problems with robotics, and actually the key is to try and solve some of them, to do exactly what Chris suggests, which is to spread that remaining workforce across those other jobs that are either too difficult or maybe not commercially viable to automate.
Yeah, there's a great example of a flower grower, and they imported one of the first robots to sort flowers and pack. And I think this was maybe 6 or 7 years ago. And the person who used to be kind of, I think, driving a forklift or was doing a task that was relatively unskilled is now running the robot. So it was an opportunity to really provide higher value jobs, better paid jobs, and that person is now a massive evangelist for the robotics. So this narrative where journalists are always asking me, they're saying, oh, well, the robot's going to displace jobs and all the rest of it. Well, yeah, the ones that people don't want to do, and give them ones that they're really excited about doing. So that's really, really fun. And in terms of recent developments, one I'm quite excited about is that last year I judged a robotics and automation competition, and one of the winners was spraying from a drone. And you haven't been allowed to do that in this country, in the UK. And actually, there's a company that has just recently been awarded the ability to fly beyond visible line of sight. So actually, you've got a machine that is now flying out of sight of the operator perfectly legally and can also spray as well. So if that becomes mainstream, at the moment it's just one company that has the authority to do it. If that becomes mainstream, that becomes a game changer for the industry.
If you'd like to hear more from this bonus episode, sign up as a supporter on Patreon by going to patreon.com/Claire Asher, and you'll get access to the full catalogue of bonus content. Next week, I'm chatting to Jane Pauline Ramos Ramirez from Delft University of Technology about bio-inspired flying robots. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.